You want me to? Okay, sure. I don't
Yeah,
know everybody here,
that.
but
Yeah.
first off, I'll introduce myself. I'm Dan Patnott. I'm an astrophysicist at the Smithsonian. I'm the operations scientist for the high resolution camera. So I work with Vinay extensively. And I will introduce Taylor. Taylor is a CXC predoctoral fellow here at the Smithsonian. He works with me on supernova and supernova remnant studies. And he's also a graduate student, a finishing graduate student at George Washington University, where he works with Alexander Vanderhorst on GRBs. So Taylor's been with us here at the Smithsonian for, I think it'll be 3 years come September. So anyway, take it away, Taylor.
So you can share your screen, I think, Taylor.
Yeah.
Okay, everyone can see me. Everyone can.
Oops.
Oh.
Yes.
Wrong
Oh.
button. Sorry about that. Let's try that again. Okay.
Yeah.
Okay.
It's good.
Well, thank you for that introduction, and I just want to say a thank you for inviting me to come here and talk today. And before we begin, I just want to acknowledge all of my awesome collaborators who have helped produce a lot of this work and just really kept it on track and made it what it is. And so today I'm going to be talking to you all about exploring the parameter space of high energy stellar explosions. And as Dan alluded to, these two types of explosions that I'm going to be talking about mainly are GRBs and their afterglows, and supernovae and their remnants. But before we get too far into that, I just want to give a brief outline of where we're going to be headed on this talk today. So to start, I'm going to give you a little motivation, like why are we interested in these broader parameter spaces? What's sort of pushing us to look at modeling in the way that we're going to talk about. And then from there, we're going to talk about the physics of these particular objects, at least as it pertains to generating these parameter spaces. We're going to look at them each individually, walk through their physics, mapping the parameter space, and then using observations to figure out what part of the modeled parameter space is actually related to physical objects. So to begin, I'm just gonna, you've probably heard this several times in the last few years, but we are quickly coming into the big data era of astronomy. So we have these new all-sky surveys coming along, like the Vera Rubin Observatory, the Square Kilometer Array and its Pathfinder mission Meerkat are coming into play. We now have these multi-messenger missions with LIGO, Virgo, Cagra, IceCube, and the neutrino. When LISA flies, it'll really expand what we can see in the gravitational wave space. High cadence target of opportunity follow-up has really come a long way, especially optical and X-ray have been very quick follow-up for a while, and more recently radio observations have been coming to the point where they can very quickly follow up on target of opportunity alerts, which has been a boon for GRB afterglow modeling. And we also are getting to the point where we can do fairly accurate rapid multi-messenger follow-up, like the recent gravitational wave event 170817. And then even beyond that, we have several missions in the X-ray space for high resolution X-ray spectroscopy slated to fly in the next decade or so. Like CRISM and Athena already have coming launch dates, and Lynx is in the planning stages and hopefully will be accepted to fly. And these will give us an unprecedented view of the X-ray sky and potentially give us a lot more observations and a lot more objects to look at. Now, because astronomy is a very visual science, I wanted to give some indication of what that looks like on the sky, but also wanted to just give a quick warning that there are some flashing images in the next slide. So on the right-hand side, we have the first 5 or so years of SWIFT observations. So there are 500 GRBs going off in 5 years, and then you have to extrapolate this out because SWIFT is a almost 17-year-old instrument at this point. So there are a lot more GRBs beyond what is being shown here. On the left-hand side, we have the first 6 or so months of Zwicky Transient Facility supernova observations. You can see there are a lot of observations going on that front. And then on the bottom right-hand side, we have an image of the galactic center from the Square Kilometer Array Pathfinder Meerkat. And you can see that there are a lot of resolved remnants just in this one snapshot of one smaller frame of that image. And Square Kilometer Array is hoping to take an all-sky image almost nightly. So there's going to be a lot of data coming our way. There's going to be a lot of new objects discovered. So it is really important that we are able to model them. And this poses a bit of a problem for the more traditional method of modeling supernovae and their remnants and GRB afterglows, because these objects, oftentimes the method was gather all the data you can possibly have on one particular object, take a model, fit it to that object, and these models usually did a really great job of fitting these particular objects, but they were often quite fine-tuned for the object in question. So when you move to something else that's still like a supernova remnant, still an afterglow, you had to change your model up to properly model this new object. And again, you could set it up so that it worked well for that object, but you now had systematic differences in the models that you were using. So it was hard to directly compare the two. And then you also have the issue that this is a fairly inefficient method of having to individually model every remnant. So what we are looking to do is, instead of fitting our model to data for an individual remnant, we're looking to create a more general model, like a parameter space, like a model that covers a large swath of this parameter space of these explosions. And we can then fit a lot of these objects, these observations, to our models. And then instead of having to look at each one individually, we just have to tackle, okay, why are there certain outliers? And that's a much more efficient way to explore like afterglows, supernova remnants, and stellar explosions more generally as like a class of observations and objects. So to begin, I'm just going to talk a little bit about the physics of GRB afterglows, and we'll start here. So a GRB afterglow is the result of some central compact object, some central engine. It could be a black hole, it could be a magnetar. For our purposes, it doesn't matter too much what is actually driving the GRB in the afterglow. All we care about is that it launches some relativistic jet into the ambient medium or the circumstellar environment. And what will ultimately happen is that jet will come in contact with the ambient medium some distance from the central engine, and that shock that is produced will emit across the electromagnetic spectrum from high energy gamma rays all the way down to the radio. In the case of the canonical afterglow regime, it's usually X-ray to radio, but there have been recent detections by instruments like HESS and MAGIC that have covered this high energy regime as well. Now, to model this physically, we really need two key components. So the first part is the dynamical model, which historically has been a self-similar relativistic blast wave model. You take a conic section of that to simulate the jet. But more recently, we have gotten to where computational modeling allows us to look at scale-free hydrodynamics to actually model the jet in 2D. And the neat thing about the scale-free hydrodynamics is you can scale all of the afterglow parameters except for the opening angle. So you can generate a grid of models just based on the opening angle, and you can get any other jet from that grid of models. From there, you then need to couple some sort of emission mechanism to actually to the jet to actually determine what the afterglow emission looks like. Now, the main one is synchrotron emission, but Synchrotron-Self Compton also plays an important role, and we will talk a lot more about that in the next few slides. And you could argue that there are other non-thermal and thermal components, but these tend to be quite rare and unusual. And so in keeping with the theme of we want a parameter space that will cover a lot of afterglows reasonably well, we don't really consider them here. In general, afterglow modelers tend to pair their favorite dynamical model, whether it be a blast wave or the hydrodynamics, with synchrotron emission, and then they often will invoke Synchrotron-Self Compton when synchrotron fails. But if we're looking to model our afterglows as a class of object, we really need to include both of them all the time. And the reason for that is because the parameter space will change, and I'll show you exactly why in the next couple slides. Now, just before we move too far into the actual implementation, I want to go over some of the basics for Synchrotron-Self Compton emission and Synchrotron-Self Compton cooling as it pertains to GRB afterglows. So at its most fundamental, Synchrotron-Self Compton emission is the upscattering of synchrotron photons, so photons emitted by electrons through synchrotron radiation, off of that same emitting population. its cooling term goes with the same Lorentz factor dependence as synchrotron emission, but it has a different coefficient, so its dependence isn't identical to synchrotron emission. But when it matters, when Synchrotron-Self Compton matters, it and synchrotron only cooling scale in the exact same way, which is important to note. So there's obviously the emission from Synchrotron-Self Compton leads to an additional emission peak in the GRB afterglow spectrum, but that tends to fall at those higher energies and sometimes even between the energies that we can really observe. And so we don't treat that as directly. But the other interesting thing is that it leads to increased electron cooling, which changes the spectrum in the X-ray and the UV band, which is important for the canonical afterglow regime. This has been well established in the theoretical literature. Like this isn't something that's wildly out of left field for afterglow modeling, but it's only really been hinted at and deployed when it's been needed. So if a modeler couldn't get synchrotron to work, they will then turn to like Synchrotron-Self Compton cooling or emission. But again, it's important to include because it will change how the afterglow fit parameters end up falling out when you perform a fit on the model. So when we actually went about implementing it, the idea for implementing it is fairly straightforward. You just change how the cooling Lorentz factor of your electron population changes. So it goes as 1 plus the inverse Compton parameter y, which is just the ratio of Synchrotron-Self Compton to synchrotron only power. And we consider this in 2 regimes. The first, which is the top right here, was assuming that you could have an arbitrarily energetic photon scattering off an electron elastically, and you get these very high values of y, which aren't necessarily the most physical because you have to include the fact that at some point the electron and the photon have similar energies, and so they no longer scatter elastically, and that's what leads to this bottom plot, which is the more physical reality. But even in this case, you end up with the Synchrotron-Self Compton parameter, the y parameter, being like an order of magnitude larger than the synchrotron emission, especially out to a day. And that can really change the afterglow parameters, and it can really change how the light curves look.
So sorry, can you tell us exactly what you're plotting on this? Because this is time versus the number, or is this just cooling, or what is on the light curves exactly?
So these are basically, this is the y parameter is the integrated power of the Synchrotron-Self Compton emission versus this synchrotron only emission.
Mm-hmm.
And it also works as a cooling term for our electron spectrum.
Okay, so that's kind of what goes into your model. It's not directly observable at this moment.
Correct.
Okay.
Yeah. This is
what do the KeV and the GeV mean?
So the Klein-Nishina effects have a frequency dependence. So in the KeV range, you end up with more Synchrotron-Self Compton cooling than in the GeV range, because most of the GeV photons cannot efficiently scatter off of the electron population. And then in the upper case, what's happening here is at very late times, the gamma C, so the cooling Lorentz factor and by extension, the electron cooling frequency is approaching the KeV band, which is why Y drops off faster in the KeV than in the GeV. Yeah. And then, so just to hammer home, the key takeaway here is that SSC can be, especially as a cooling parameter, so SSC cooling can be quite important in the first day or so of the afterglow. And we can really see that when we then move on to this slide, where we generated a bunch of synthetic light curves for a mock GRB observation, so an afterglow observation covering both an on-axis case and an off-axis case. And the key takeaway here is if you fit this data, which includes Synchrotron-Self Compton cooling with a synchrotron only fit and a synchrotron plus Synchrotron-Self Compton fit, which the Synchrotron-Self Compton fit is blue, or solid, sorry, is solid, and the synchrotron only fit is the dashed lines. And there were a couple of interesting things that came out of this. So the first thing is that the optical doesn't really seem to mind whether or not you invoke this. which makes sense because it's not really dealing with the cooling frequency in a meaningful way. The X-ray cares a little bit, as you can see if you look at the data points, there is this rise, which they both struggled in some sense to capture, and we'll talk a little bit more about why that is in the next slide. But the big takeaway here is that the radio fits, especially in the on-axis case, were quite different. And that's really that is something we see a lot when modelers attempt to model these afterglows, is they end up with very strange radio fits. So that was quite interesting.
So, yeah. So can you say exactly what's on these graphs? Because there's like a number of parameters at the third line, and then are those your simulated data fitted to observed data, lightcurves? Explain a little more, please.
Yes, of course. So that's exactly it. So the data plotted are the simulated data, and then we took our simulated data, chopped it up in such a way that we had a observing cadence start time that was consistent with the observatories available, and basically a continuing cadence. So the number of observations and the spacing between these observations, that was more or less consistent with what like Swift XRT or ground-based optical telescopes or the radio band could conceivably do. And then we took the base box fit and applied the fitting algorithm that comes by default with that code. And then we took our modified version of box fit and applied it to the data as well. And these light curves represent the output of those, like the best fit model for those. And
so this is the simulated data, assuming different observing time for different in different waveband, right? And then you're fitting this with your model, which is the SSC, Synchrotron-Self Compton model. And then there are these parameters, right? So these are the parameter of the physical model, right? Particles and densities and energies.
Yeah.
Okay.
Here, and I'll just run through these quickly. So we have the initial electron power law index, the fraction of the energy that's in the electrons, like the fraction of E iso that's in the electrons, fraction of the energy that's in the magnetic field, the circumburst density. In the case of a wind medium, this is set at 10 to the 17 centimeters, so the density at that distance from your central engine. This is the energy, the isotropic equivalent energy. So if you assumed that your beamed energy in the afterglow was coming from an isotropic like blast wave, this is what the energy you would estimate. The opening angle, so how wide the jet is opening, and then how the observer angle, so where you are relative to the center of the axis. And then there's also an electron acceleration efficiency, see. And now in the case of these two models, the only difference between their parameters is the opening, or the observer angle is 0 on the left and is equal to the opening angle of the jet on the right.
Oh, okay, that's what means on axis and off axis. Okay.
Yeah, sorry about that.
All right. Yeah. No, it's okay. I just
I have a question. So, when you generate where does the simulation come from? What do you use to do this to make the simulation?
So we used our initial modeling code to generate like a high resolution light curve, so one that had a very narrow time base. And then we basically took a random sample based on the observing cadence. So we set some initial time, we then set some minimum time between observations, and then we took that data and added
But you're assuming some sort of an emission mechanism for the process.
Yeah, so we are assuming that our synchrotron plus Synchrotron-Self Compton model is reality in this case. Okay. So I guess what we're really trying to get at is if this is really what's happening, which it makes sense that it would be, again, because if you have synchrotron emission, you should have some level of Synchrotron-Self Compton cooling, just by nature of the fact that you have synchrotron photons and synchrotron electrons moving near each other. So if we assume that is what's happening physically, this allowed us to understand, well, how is this going to then change the derived parameters if we are trying to fit the wrong physical picture?
I don't know if I'm jumping ahead, but it seems to me that the model, including the SSC, is recovering the parameters correctly. Is that right?
For the most part, and we will I could actually move on to the next slide here. So this is these are three non-degenerate ratios that come out of boxfit. So there is some degeneracy between parameters, but these tend to be when you perform a fit, these parameters tend to be fairly insensitive to specific degeneracies in the modeling. And you can see that in the off-axis case, which is why I point this one out, because if you look at the off-axis case, you just by looking at the light curves, aside from the X-ray and the UV here, these light curves actually do the synchrotron only model does a fairly decent job of recovering the light curves. But if you look at the parameters in the case where our observer is along the edge of the jet, the synchrotron only modeling code believes that we are exactly on axis. And it also inverted the values of epsilon E and epsilon B. And it gave, oops, sorry.
No.
And then we also had a significantly different ratio for E ISO over N naught, which these vertical black lines are our expected parameters. So this is what, assuming our fitter was perfect at recovering the data, this is what we would expect to see. And in the on-axis case, again, the synchrotron only cooling decided that we were severely off-axis, so right at the edge of the jet, whereas the synchrotron plus Synchrotron-Self Compton cooling had us closer to where we were supposed to be, but we didn't quite get there. And again, it does a better job at recovering the other two parameters as well. And you see something similar where the opening angle seems to be difficult, the most difficult thing to recover, or at least this ratio seems to be quite difficult to recover by the fitting mechanism.
So I have a question. What are these distributions, or how do you get this histograms out, right? It's not just one value, which is the input value, right? Right.
So these are based off of as boxfit runs through its fitting algorithm. It is a downhill simplex model that uses simulated annealing. So it kind of steps through parameter space, and every time it takes a step, it generates a best fit for that step or that iteration. And so this is a plot of all the best fits as we kind of tumble towards the converging towards the solution that it felt was the most precise, or the best recovery of the parameters.
So the distribution is not really a posterior probability distribution, then, right? It's just whatever the algorithm, the optimization routine did.
Right.
However, it got to the best fit.
Correct.
Can we tell from this plot where the best fit actually is? Is that where the peak is, where it spends most time, something like that?
Yeah. So in general, it tends to be where the peak, at the peak of the distribution, which is promising. But in this case here, it actually the best fit is at this slightly smaller peak as opposed to the slightly bigger peak, which
yeah.
And what are you using for the what's the word, the chi-square equivalent? I mean, what is being minimized exactly?
So this is minimized. So it's minimizing the value of this. So if we go back to this pledge, the chi-squared is the data value minus the light curve value at that time bin divided by the error on the data, on the input data.
So it's okay, chi-square minimization. Okay. And across all the different frequencies, wavelengths that you looked at for every time bin.
Yeah. So it minimizes over the entire data set at once. Yeah.
Do you really need to, I mean, so right now, for example, there is more, I mean, this is a problem that we have faced before with this group, where you have more data from X-ray and gamma, right? Fewer data from radio. aren't you worried about the fit being biased by making sure that it fits the X-ray and gamma ray better?
Yeah, so that is a very real concern, and this is something that we have talked about at length, trying to find ways to like kind of get around the fact that the optical and the X-ray sort of dominate the fit, because they have like there's a lot more of it, and the error on these tends to be a lot better or a lot smaller. But as we found out, the radio can be is oftentimes the most constraining data, which is interesting. There have been a few different things proposed. We haven't necessarily played with them all directly. In most cases, we've just looked for well-sampled radio GRBs is where we've started, and along with like any like particularly interesting burst. And
Thank you.
yeah, no, that is definitely an open problem though. Like how to best deal with the fact that radio is kind of missing compared to the other bands. Yeah. But then just to come back quickly to the fitting, and to move on to the next part, as we've moved on to going from modeling the synthetic data where we at least know what the input should be, and moved on to modeling real data, we've spent a lot of time trying to optimize the incorporated fitter in boxfit and trying to get that to converge in a more reasonable way. But it seems to really struggle with dealing with the parameter space, like to walk in the parameter space in a efficient method or in an efficient manner. Like it takes a very long time for it to converge in a way that we really feel comfortable with when we don't know what the output parameters are. So we very recently moved on from this fitting to a fork of boxfit that has been produced that uses multi-nest instead of the downhill simplex method. This is a fairly recent development, so we've been doing some work testing it versus the older method of fitting in boxfit to understand how it changes things. It seems to do a better job of converging, but one problem we do have is that an individual fit iteration takes longer, because instead of moving around the way the downhill simplex method does, where it calculates one point in parameter space and walks it so it can do the light curve calculation in parallel, which is the longest part of a box fit step. It then it does multiple light curves at once and chooses the best fit from that group, which is a slower process. But so just to quickly summarize before we move on, in the GRB Afterglow case, we have these physical models that we can use to kind of map out the general parameter space of observed GRB Afterglows. And we've been able to take advantage of the fact that this, some of this work has already been done, and we've been able to just kind of fine tune this modeling so that we feel like we are accurately capturing the statistics, the physics that's going on, and we are able to produce these pretty reasonable physical maps of parameter space. And now we are moving on to applying these to data to actually understand where the afterglows live in our space. And we can do something similar for supernova remnants.
I'm sorry, before you go on, can I just ask about the going from chi-square fitting to multi-nest? That's kind of a bit of a jump, right? Because for multi-nest, you're doing Bayesian inference, you need likelihood functions. These are counts, right? So I guess you'd be using Poisson likelihoods and prior distributions. This says, do you worry about the likelihood and the priors for your multi-nest?
That is a great question. Like I said, we are just beginning to dig into this and really understand what's happening. By all accounts, it seems to do a reasonable job of extracting the results, especially in.
So, but so multi-nest, I think it's going to give you a sample from a posterior distribution, right?
Right.
But what is that posterior distribution? I mean, it's a different. There's things you need to add to go from chi-square fitting to posterior distribution.
That's a great question. So that's something I can't answer that question at this exact moment. I'd have to look back at the code and double check it before I told you exactly what was happening, because I don't want to mislead you or misrepresent what the fitting is actually doing.
Okay, I mean, isn't it true that I mean, you're still fitting to the fluxes, right?
Yes, that is correct.
So you're basically using, I mean, the likelihood here is just e to the minus chi-squared by 2, right? I mean, is that what you'll be using?
I think so. I apologize. It's been a little while since I've actually looked directly at the code, but that sounds correct to me.
Well, I guess David was not asking about the code, is asking about from chi-square to base, you fundamentally change the model. This is how to implement is one thing, but how do you model the process, right, from the data to your conclusion? And
Right.
chi-square fitting is very, straightforward, but on the hand doesn't have all these benefits of the statistical modeling. I think that's what I was. I think so. It's really the question about what was putting down that moving from a chi-square to the base. You need, as David said, you need the likelihood, maybe Poisson, you need the pri. You guys must made a lot of choices. How do you set the pri, which you don't need it when you do chi-square fit, right? And these choices will matter in terms of whether the thing's working or not. That really has very little to do the code implementation.
With the specific implementation.
Right, but that's I think what we obviously asking as a statisticians, right? That's what we care about. We're saying, okay, how do you say the pri? How do you say so? That's a part of that we'll be interested in, that help us to think about how you're improving, and if anything we can suggest to help to improve. Yeah.
No, that is very fair. I'm sorry. I am very much I consider myself a modeler who does works on astrophysical problems, so I tend to come at it from a computational perspective, but I understand the question now. Initially we started with just a flat prior, and we've just been kind of iterating on that. I don't really know if we've come up with anything better yet. Again, this is still very early times for the implementing multi-nest.
So by flat, you mean just between the range of the I don't know, the density of the fluxes you expect, so it's flat within that range? Or yeah, probably.
Yeah, I'm pretty sure
it's not from infinity to infinity, right? You have some restricted range of the parameter values. Probably.
I'm sorry, you were all asking very reasonable questions, and my brain is just going blank right now.
No, it's
okay.
It's okay. We completely understand, but I think just to give you possible ways you can improve. For example, when we talk about flat pri, right? Then the question from statisticians will be asking you go flat on what scale? For example, you can flat on the Poisson intensity. And we tend to don't do that. We be flat on the log of intensity, right? And and it's equally simple, equally complicated to implement, but you got different results. And I think that's what matters. And so that's the kind of things that we hope that we can, at least remind you to look into this different flatness. And usually we do some transformation, get rid of the boundary. Intensity is positive, take a log, you get rid of that. And if you have anything between 0 and 1, we do a logit transformation, get rid of the boundary, just to make this flat pri. There are reasons, theoretical reasons, we don't have to get into it. But there's a few easy things for you to try without complicating your implementation, but you might be surprised to see how the results may change, which of course is also disturbing, because just simply, thinking about some flat pri, you get different answers, but you should be aware of that.
No, that's fair enough. That sounds entirely reasonable.
Can you put up your plot of that comparison distributions that you showed before? Yeah, that one. So the theta obs over theta naught, is that, for example, limited to between 0 and 1? It seems. I mean, what is? It seems that the distribution actually spreads out beyond 1.0, right? What does
So
that mean exactly?
so this angle can actually go to, at least you could like this angle could actually go to 90 degrees to the jet, which basically means you would see almost none of the afterglow for the majority of the afterglow's lifetime until you started to see the lateral spreading of the jet. But like technically you could be looking at a GRB like perpendicular to the jet. So we did allow the fitter to go to that parameter space. It didn't wander very far because the emission drops off quite steeply once you're outside of the opening angle of the jet. So it was able to pretty reasonably figure out that it needed to move back towards like being within the jet opening angle.
No, my question was much simpler. So what's the possible range of the theta offs by theta naught that you have in the problem?
The plausible range. So it would run from 0 to, let's see, so theta. So it would run from 0 to about pi over 2.
Pi over 2. Okay.
Yeah, roughly pi over 2.
Okay.
Yeah.
Okay. So I know, essentially, this was a follow-up to what Anita was asking about. If it's flat, then you would assume that it's anywhere between 0 and pi by 2. I thought you had 0 to 1 here, but never mind, my mistake.
Sorry. Yeah, like I plotted over 0 to 1 because going all the way to pi over 2, these distributions shrink down. You kind of lose some of the definition, but it can theoretically go much further away. Yeah. So anyway, so walking back through the GRBs just to remember where we've come from. So we've kind of set up this this pipeline, this framework for understanding afterglows as a class of objects, looking at the physics, looking at what emission can come from like modeling that physics properly, and then ultimately trying to understand how that connects to what we are observing. We can do that in a similar way for supernova remnants, with the caveat that like we don't necessarily have a box fit, like complete understanding of the physics in one single code. There are a few different codes that we can use to properly model the remnants, but we have to spend some time pipelining them together. Now, in the supernova remnant case, we have to consider the fact that because these explosions are much lower, like they're lower energy, lower velocity, that jet, which in the GRB case is getting out into the like 0.1 parsec scale and is getting quite far away from that central engine, and is largely composed of electrons, and like they are more or less dictating how the jet is playing, like how the jet is behaving. You have to consider the interplay between the progenitor, the CSM, and the the remnant shock, and that makes things a bit more complicated. But we can set up our physical model in a similar way, where we have our remnant on the right hand side here in a core collapse supernova remnant. So one formed from a massive star, we are going to have some sort of central compact object. We will then have the ejecta from the explosion, and we have that same forward shock region. Again, it's much closer to the star, and instead of having just a jet, we have a more or less spherically symmetric shock wave, which is shocking the CSM. And then we have the shocked ejecta, which plays a bigger role in the remnant emission than it does in the later stages of the afterglow. And that's the reverse shock there, shocking the ejecta. And then just to give you some idea of what these remnants tend to look like in the sky, this is, as my advisor says, everyone's favorite supernova remnant, Cas A. We're not going to talk too much about Cas A because, as you'll see and probably already know, it's a bit of an oddball. But
I think there is a very strong, very narrow prior distribution there when he talks about everyone's favorite.
I suppose so, but it is a very photogenic remnant. I think we can all agree on that. But so now to talk more broadly about how we are actually setting up this pipeline, setting up this like our software so we can model this parameter space. So like I mentioned previously, the remnant, the supernova, and the progenitor are all kind of connected. How earlier stages of the star's life play out will dictate how these later stages play out. And so we have to consider the entire chain and not just the final object. On top of that, stellar parameter space is quite large. There are a lot of uncertainties in how certain physical mechanisms play out. There's a high degree of degeneracy in how you can set your parameters. But so we've worked to kind of take a broad sampling of single star models in this case. So like in the case, we use the MESA stellar evolution code to generate a fairly robust grid of single star models ranging from about 9.5 to 30 solar masses. We would have liked to go lower, but our nuclear reaction network struggled to deal with the certain types of reactions that happen at lower masses. So that's something we'll have to come back to. And we worked hard to make sure that our modeling code was based off of MESA test suite cases so that we could modify them, and also that we had a reasonable expectation that they would produce stellar output over a wide range of masses. Another thing that we considered was the mass loss of the star. So how the star loses mass before it explodes will affect what that final CSM looks like. And that was a very important thing to consider when we were generating this pipeline. So here on the left, we have a few plots that kind of show off what the final progenitor distribution looked like. Now I'm going to focus mainly on these bottom two plots. Where we cover the different mass loss mechanisms that we used, and we compared them against derivations for the various supernova progenitor types. So based on the hydrogen envelope that was left at the end of the star's life cycle at iron core collapse, we were able to use that to kind of discern what the probable progenitor type would be, or the supernova type would be, from Namoda et al. And our values are in reasonably good agreement. So we see our 2Ps end at around 20 solar masses, which 18 to 20 is usually the quoted cutoff for 2Ps. Our 2Ls extend a little bit beyond that. And then beyond that point, we have our 2B supernovae. And again, this is where Cassay kind of comes in with its oddballness, is that we expect that to be a much smaller progenitor, probably a merger or a binary interaction. Yeah. Which is why we don't really talk about it here, because these are all single star models.
So can I ask a question here? So when you plot these masses, is this the input to your next step, or is this just the result of some pre-processing you do? Just try to understand what it means.
Yeah, so this is part of that final progenitor composition over here on the right. So that's what we are looking at. So when we get to iron core collapse in MESA, we have the composition of the progenitor. We have thermodynamic information, dynamical information, composition information. And so we can, before even going on to the next step, we can look at that and see how we are stacking up, and that is a good check to make sure that we don't wander off into incredibly unphysical parts of parameter space by the time we get to the end. Yeah. And then just as another point to make, you can see that the hydrogen envelope changes significantly depending on the mass loss mechanism that we invoked. So in the case of the solid blue line, we had a rotating star with a MESA default Dutch wind scheme. In the orange curve, we had no rotation, and these lines match each other pretty well. They're just shifted slightly because you get that enhanced mass loss from the rotation. And then this last one, it uses a Van Loon wind scheme, which is a dust-driven wind. You can see that we have a significantly smaller hydrogen envelope, but we don't talk a ton about this particular mass loss case because its applicability is limited, because our stars spend a good portion of their time above the interpolation range of the Van Loon winds. But it's important to note that dust-driven winds can theoretically give you higher mass loss rates. And then another interesting thing to know is, in spite of the fact that these have very different hydrogen envelopes in the end, their carbon-oxygen cores are relatively similar, and these regions are derived from measurements of the iron versus silicon abundance ratios of various supernovae and remnants, or various supernova remnants, and our models again like fall pretty nicely in that range. So that was another nice vote of confidence that we are moving along in a physical direction. And then to just really quickly touch on the CSM. So most of our models were more or less very well-behaved red supergiant stars at the end of their lives, with some exceptions. And we were able to produce a CSM density that looked more or less like one that would be constructed by a stellar wind, with the 1 over the distance squared dependence on the density. And we were able to then take the average mass loss rate over the last 500,000 years and use that to construct a CSM density. And again, we once again compared that to observational measurements of various supernovae, and we were able to confirm that our models were within expected parameters, both in the CSM densities and in the measured mass loss rates at the end of the star, at the end of the star's life. That was pretty nice. From there, we moved on to SNEC. Now, on the SNEC side of things, we had to do a fair bit of calibration to make sure that our models were exploding in a reasonable way, because there are several free parameters you have to tune. And so to do that, we compared that to the literature, in this case, a paper by Young and Fryer. And we tuned our explosion parameters such that we were able to generate reasonable agreement with their output, with the notable caveat that they have a much bigger reaction network. And so we have things like our magnesium, for instance, is much higher than their quoted magnesium, because of the fact that our network has a known issue of producing more magnesium than we would expect, which doesn't affect what we want to do with these models right now, but is something that needs to be noted, because going back, if you want to look at magnesium more closely, you need to consider that. Finally, once we have our supernova evolved out to about 100 days, so the end of nickel and cobalt decay, and once we have our CSM, we could take both of these and put these into the cosmic ray hydrodynamics code to simulate the full behavior of the remnant. Now, this is a 1D simulation. We get the full NEI information, shock velocities, thermodynamic variables, and it outputs supernova remnant emission in the form of thermal spectra with the line emission from AtomDB, and also non-thermal spectra. We don't really do much with the non-thermal spectra, but they are an output that could be used depending on what you were interested in doing with this pipeline. So in that output, on the top left, we have a small section of three different progenitor objects from the pipeline. So we have about a 16 solar mass star, a 20, and a 27 solar mass star. And these three objects are exploded into two different CSMs, one where the mass loss was set against a 5 kilometers per second wind, and one where it was set against a 15 kilometer per second wind, to generate two slightly different densities. And you can see there are differences both in the overall luminosity of the spectrum, but also in the number of satellite lines that you would see. So this is helium-like iron here, and this is iron Lyman alpha here. And so you can see subtle differences in the line energy, the individual line energies and the satellite lines. And now this whole complex is often referred to as iron K shell emission, as you can which you can see down here in this Chandra spectrum of this is Kepler supernova remnant. So this is this peak here, and because of the iron K emissions relative isolation from all these other peaks in the spectrum, it's a very tempting target to use as a diagnostic. And one of the things that you can do with the iron K centroid is use it to discern progenitor type. So you can use the iron K centroid to discern between whether you have a type 1A progenitor, which are these points over here that don't have any markings on them. And then these points here are observed core collapse remnants. And this blue region is the forward shock emission of our model. And with one exception, which the iron detection is a little low in that model, but I won't say anything more on that. All of our models fall outside of the 1A range, and they capture most of the core collapse models reasonably well, which is exciting and a very interesting result. And one other important thing to note is that the iron K centroid tracks very nicely across its centroid energy. So as the centroid becomes harder, we can follow this as the mass increasing. So if you take your lowest mass, like your lowest SAMS mass model will be somewhere down here, and it will track upward on this trend until we get to our 30 solar mass stars up in this region. So that is very nice if you want to do some inference on like how large your stars are, or potentially how old they are. But there's one key problem with the iron K centroid, and that's not every remnant has like iron strongly emitting in its spectrum. And so another thing we attempted to do was look at the sulfur, like so helium-like sulfur emission, which is in this region here. But sulfur runs into a couple of problems. First, it's in a much more crowded part of the spectrum compared to iron. So you have to deal with helium-like and hydrogen-like sulfur, helium-like silicon, like this whole mess of complexes in the 2 to 3 keV region. And then there's also the issue of sulfur has a lower atomic number, so it is more easily ionized to higher energy states. So in some of the higher mass models, we actually have the issue of sulfur being ionized beyond the helium-like state into the hydrogen-like state, which poses a problem and gives us this much more complex data, like this much more complex region than what we saw with those very smooth lines in the iron spectrum, in the iron case. Now, one thing that my advisor Dan suggested that we could do was use Gaussian mixture modeling to potentially disentangle what the underlying distribution looks like, so we could assign probabilities to like some of these data, or at the very least understand approximately where these models like fell in our distribution, like relative to the progenitor masses. Now, this had the added benefit of allowing us to fill in a lot of the gaps in our data, because using this model allowed us to maintain the same density of points for each individual input, but it allowed us to generate an arbitrary number of points, so we could then better understand the parameter space. Now, the inputs for this particular model were the sulfur luminosity, the centroid energy, the SAMS mass, and the remnant radius. And again, like with this in mind, it does another a reasonably good job of reproducing what we see in literature with these particular remnants, which is useful. And it also gives us a way to, as we move forward, to quantify the uncertainty that we have on these remnants. So how likely it is that one of these remnants connects to one of our models. So it's a pretty awesome step forward. So then from there, we can also talk about the absorption within the remnant, because these are like 3D objects. And so depending on where your emitting region is within your remnant, you're going to have absorption from the rest of the remnant. And this is something we can model in CHN based on the ionization and the densities that we get out. And this actually comes in a very timely point in history, because I don't know how much any of you follow the supernova remnant news and pulsar wind nebula news, but there have been a few papers going back and forth in the last couple of years about claim detections of the central compact object of 1987A, and then rebuttals of that detection, and then new detections and new rebuttals. And so with this absorption calculation and with our models, we can then take sample pulsar wind nebulae, sample compact object spectra, and look at their time evolution and compare that to the shocked emission and see, based on how bright the shocked emission is and how much absorption we would expect from our models, how likely we are to actually be seeing the pulsar wind nebula. So that's a cool thing, and that's something that we are very quickly moving towards. And then finally, I just want to take the last couple slides to like be more forward, like look forward a bit. So one thing we really need to do to expand CHN is to expand the parameter space. So we talked about how these are all single star models. They mostly look like red supergiants. There are some changes we can make because some of our models exhibit blue loop behavior. So we would expect high velocity, slightly lower mass loss winds in some of these regions. And that would make a much more complex CSM, which we are planning to go back and examine further. And then on top of that, at the lower end, there's also wave-driven mass loss we have to consider, which is much more episodic and can lead to very large shells moving at relatively high velocities towards that are fairly close in to the progenitor. And then finally, I mentioned these at the beginning of the talk, and I want to make sure that we circle around to these objects again. So we have those X-ray microcalorimeters, which are going to have great spatial resolution. You can see here's a Simplex observation of Athena and Chrism plotted against a rough approximation of an A6 spectrum. Like this is actually a 100 EV Gaussian convolution, so it's not quite an A6 spectrum. But you can see that the spectral resolution, is significantly better. But this comes at a cost of fairly low spatial resolution. So a lot of these remnants, anything beyond like 10 kiloparsecs is going to be more or less a point source. So how do we extract data from this? How do we understand the remnant? Well, one thing we can do is we can use this higher spectral resolution to look at things like the helium or the hydrogen-like to helium-like line ratio. So that's what we have plotted on the left, and we use that for the integrated spectrum of the entire remnant. And we do see some trending based on the progenitor object and the age. But another thing we can do with our models is we can use that same absorption principle to understand how these remnants would look along the line of sight. So we can use the fact that the redshifted emission is coming from the rear of the remnant, the side opposite the observer, and is going to be preferentially absorbed to like map out what the absorption within the remnant looks like, and what then from there determine more or less what the 3D structure looks like. And so like this is something that we are working towards and seems to be working quite well. So I will leave my summary slide up here and see if you have any questions. Thank you.
Thank you.
Thank you.
Are there any questions? I have a couple, but let's. If anyone else has questions, they should probably go first. If not, then let me ask this question. So I was confused by how exactly you're using the resolution of Chandra in this work. CASA is very nicely resolved, right?
Mm-hmm.
But then it seemed to me that you're using one spectrum and one measure of the centroid of the INK to figure out what to build to do all the fits and everything. So am I missing something here? What is the what's the extra bit?
The extra bit. That's okay. I think that's a reasonable question. So at least in the these initial phases of building the pipeline, like of course we can take these spectrum and you pass them through like a response matrix and use them to perform fits on broadband like A6 spectrum. That is something that we can do, and we did look at that and look at a few example remnants, but the way everything just sort of progressed, it seemed to make more sense to look at the centroids, especially when we're comparing to prior work and when we're trying to also loop in conversation about like 1As and like where we can go from here.
But wouldn't your spectrum be some sort of weighted average of different temperatures across the remnant? And if you have parts that are maybe lower temperature, you would shift the centroid to higher energies and vice versa.
I suppose that would be true. I think one issue that we have here is we do have a spherically symmetric remnant. So the emission, at least in this case, is dominated by, and like most of these plots, is dominated by emission from that forward shock region, which is more or less homogeneous because of that spherical symmetry.
Okay. Dan says that turns out not to matter.
Well, I guess because of the resolution we have.
Maybe
I don't
because
know.
of the resolution. But then, yeah, if you have
Not matter because you're comparing something that's a weighted average of a bunch of spectra in a real supernova remnant to a model that is also some sort of average
Yeah.
of
average
spectra from your model. So it actually washes out in the end. Sorry. I shouldn't speak over Taylor, but that's kind of how it works.
Okay. So it's a very complicated physical model of the entire process of making the star, evolving the star, getting the winds, and then exploding it, right? So you have all these steps in your physical model. And then, you were showing us all the possible coverage of the parameter space where you try to test all these models. So yeah, selecting. So I don't know if you actually thinking about now the selecting or constraining the parameter space and seeing which models fit the data which we have, like the given supernova remnant, like Kepler or Tarka or whatever. So do you have some ideas of what and how do you do that when you have the physical one?
So that is something that now that we have the models, and that we are in a position where we can feel like they are reasonably representative of reality, that we can start doing a deeper dive into connecting them to like these physical models, or connecting them to observation. So we have done that to some degree with these more qualitative comparisons, and then like especially with the Gaussian mixing, hopefully we will be able to make more quantitative assessments of like the probability that a given like progenitor object likely gave rise to this remnant. And like that is like the path that we are starting to explore now. Whereas like in the most of the prior work has been, how do we like reasonably describe this parameter space in such a way that we have the underlying models to actually begin doing this work.
Yeah, so this is the beginning of your probably statistical model. How do you now develop the statistical model which connects your simulated physics into the observed reality, right? Yeah.
Right.
So you started with this, looking at the lines, but can you envision doing this in like in spatial dimension as well? Because you have, three-dimensional structures. Can you think about the images which you generate? Oh, no, maybe I'm wrong.
Well, so this is something that we have actually been talking about a little bit, especially when we're talking about where's the absorption here. So like producing these like 2D, like projected 2D images of these remnants, with the caveat that they are going to be largely spherically symmetric because of the underlying model, and like like using that as like to sort of model like possibly like a rough approximation of what a remnant would look like, either like here or on some of these next generation detectors. That is something that we are really interested in doing moving forward.
So how big are those Doppler shifts? I mean, I cannot see this. Oh, this is the scale. Okay, so on the right side, you have the energy scale and the green and the red. Sorry, I just can't see on my screen. It's small.
Sorry. So like in the lower left, we have
Okay.
hydrogen like iron and velocity space. So we're seeing like roughly a shift of to like 3,000-ish kilometers per second.
Well,
So-
so when I look at the energy scales, these are very small shifts, right? In energy blue versus red, it's very small. So yeah, I don't think we can see that in Chandra.
Oh yeah, no, these are definitely something that you'd need like Chrism or Athena, something
Yeah.
coming down the pipe to really see, because unfortunately this would be more or less blurred out in Chandra.
So when you generate your models, you probably have this uncertainty on even this redshifted velocities, right? So does each model generate different type of profile, this velocity profiles? Or does it depend on the direction or the symmetry and axis symmetry of the initial ejection or explosion?
So again, unfortunately, because these are all spherically symmetric, the main difference is more in the, especially as we get along, like the real driver of how the remnant evolves is how much material is in that, like the CSM. So that will change how the shock velocities, and that's the main driver of like variations in the shifted emission.
Right, because you have the density in the medium as well.
Which actually brings me to my other question, which is you have assumed that it's that this circumstellar medium is sort of nice and smooth and symmetric. Especially with 87A, that is not true, right?
Right.
So when you say that you can predict this PWN properties, what sort of systematics do you think you'll have to deal with? I mean, how certain would you be when you do make a measurement of some sort?
Well, so that is a tougher question. I will say that a lot of the absorption for the pulsar wind nebula comes from the unshocked ejecta in the center of the remnant. So that's not going to be as as affected by the CSM and by the mass loss history as we saw from the, here I can actually pop up to that quickly. As we saw from this plot, where the carbon oxygen core, which is going to make up a lot of that unshocked ejecta, is largely the same regardless of the mass loss history. So I would say we probably still have a reasonable expectation of predicting it. I think the bigger issue would be making sure that our model accurately reflects the progenitor of 87A, which, because the medullary clad has a lower metallicity, we will have to make some allowances for that and potentially run a lower metallicity grid.
I thought the progenitor of 87A was fairly well established. Isn't that true? I mean, when you know what the mass is and.
Yeah, sorry, the progenitor is really well established. Like from our parameter space, it's a little bit outside of our parameter space because of the metallicity.
Oh, okay.
Yeah, so we'd have to really go after 87A in particular, we would have to do some additional work, but it is very much based on the models that we have produced. It is very much something that we could potentially look at. Yeah.
But that would be nice because you know what the progenitor is, right? And you can actually run through your model and see. Well, I guess you have to have the whole statistical part built in order to do that. But yeah.
87A is actually really hard to do because it was a blue supergiant, and it's really hard to get blue supergiants to explode. And there's also probably a merger of a merger. So there you go.
Yeah, but it's yeah.
So
But so maybe not super not 87A, but it would be nice to see something where we know I don't do supernovae, but if you know a progenitor and you have an expectation of what should happen, then you can reconstruct with your model the path, right, of that supernova remnant.
That's a good idea. In fact, 93J is one that you could do that with. It's nearby, and we have pre-explosion images of it.
Yeah, that would be very nice, because also I was thinking about 3D to 2D, that when you have this visualization of what's happening, it's very nice. I mean, we're looking at model space, but if you generate an image, then you can say, well, it's of course very hard to generate an image from the model like that, but one could think about it. Be nice. Anyway, there are probably other questions.
What time is it actually? To be lost my window here.
It's 1:18. We're done. If there's
Right.
no questions, I guess we're done with the main part. Oh, Young joined us. There, I see Young.
Yeah, I'm here. Sorry, I joined late.
Yeah, no, it's okay.
Yeah,
It's
that's
good to see you. We haven't seen you for a while. It's like
Yeah,
this
it's
meeting.
been a lot.
Yeah.
All right. So if there are any other questions, if there are no other questions, I will stop recording.
Yeah, you can stop recording.
Last chance. Calling once, going twice, and done.